Okay, we're going to do law of sines and we're going to do law of cosines. Those are both non-right triangle examples of non-right triangle trigonometry. Often when we're introduced to trigonometry, we're introduced in terms of right triangle trigonometry, and that's SOHCAHTOA and all that business. But the fact that most math books talk about right triangle trigonometry implies really that there's such a thing as non-right triangle trigonometry. What is that? Non-right triangle trigonometry has us deal with non-right triangles, and we can draw some conclusions from non-right triangles. Law of sines is easier to establish than the law of cosines. The law of sines says, oops, sorry about that. If we have oh goodness, sorry about that. All right, we're going to talk about law of sines and law of cosines, and those differ from a lot of what we do in our first introduction into trigonometry is about right triangle trigonometry. That's what books call it, right triangle trigonometry, which implies we're dealing with right triangles, and that's really SOHCAHTOA. But there are other kinds of ways we can use our trig functions, and one of those ways involves non-right triangle trigonometry. For example,
are you on the phone?
We can take a non-right triangle, draw an altitude in that triangle, and conclude the following. I didn't do that very nicely, but we have angles A, side A, angle B, side B, etc. And we could draw the following conclusion, that the sine of angle C using SOHCAHTOA equals h over A. We could say that the sine of angle A equals h over C. If we solve both of those equations for h, we would get h equals A sine C. And in the second equation, we would get h equals C sine A. We can set those two equations equal to each other, in which case we would get A sine, C equals C sine A. And by dividing both sides by side C, by dividing both sides by side A, we would get sine C over side length C equals sine A over side length A. By extension, we could do that same process again and prove that that is true for sine angle B over side B. That's our law of sines. Again, that's non-right triangle trigonometry. Okay. The second result we can get, so that's the law of sines. The law of cosines is a little more complicated to derive, but it's not that bad. Oops. Let's take a non-right triangle. And in fact, I'm going to make it close to a right triangle. I'm going to say this is pretty close to 90 degrees. I'm going to call that C. I'm going to call that A. I'm going to call that B. Well, you know, it looks, if it was a right triangle, it would be a squared plus b squared equals c squared. That's Pythagorean theorem. It's not a right triangle. Let's drop a little altitude there, and let's call this little sliver x. Let's call this let's call this line, this segment there, h, the height of the triangle. Well, we certainly would be entitled to say a squared plus h squared equals, oops, sorry about that. C squared. That would be from this right triangle. Well, no, I'm sorry, that's not even correct. Because that's no longer a squared. This isn't a, this here is a minus x. So we really have a minus x. I'm botching this all up. Squared. All of this is a. This piece here is a minus x. So we have a minus x squared plus h squared. That quantity there, the height of the triangle, equals c squared. Okay. So that's Pythagorean theorem. Let's try to think about how we can proceed trying to eliminate as many unknowns or variables as we can. We can define h squared. Well, let's go ahead and FOIL out a minus x squared. And that's going to give us a squared minus 2ax plus x squared. That's a minus x squared. And then we still have a h squared on the left side of the equation equals c squared. Let's think about h. And I'm going to do that up here. I'm going to think about what h is. Well, certainly by Pythagorean theorem, I could say x squared plus h squared equals b squared. But really, one of the things I'm trying to do is to get rid of x. That's sort of an arbitrary, x and h are arbitrary variables or unknowns that we've introduced into this problem from the original statement. I should say, I guess, I want to suggest I know a third thing, which is angle C. All right. So if x squared plus h squared equals b squared, then I could say that h squared equals b squared minus x squared. If I plug that result in for h squared down here, I would get a squared minus 2ax plus x squared plus, instead of h squared, I'm going to plug in b squared minus x squared. I would get b squared minus x squared equals c squared. Now you can see my x squareds cancel, and I have a squared. I'm going to reorder the terms so that I'm going to put my a squared first, my b squared second, my negative 2ax, and I'm going to say this x squared cancels with that negative x squared. So now we have a squared plus b squared minus 2ax equals c squared. Well, let's think more about x. Now, I'm not sure how we've kind of lost part of our drawing up there, and I'm not sure how to pull that back down. But that drawing was that A represents everything all the way like that. So this is really A minus X. That's H. That's B. That's C. And this is angle C. Let's think about X, how we might define X in a different way. Well, I have angle C down there, and the cosine of angle C is in fact equal to x over b. So cosine C equals x over b. And I could define that for x by saying x equals b cosine C. If I replace my x over here with b cosine C, I have a squared plus b squared minus 2ab cosine C equals c squared. And that's the law of cosine. I mean, it's not a super easy proof, but it's not evident. And certainly if you've done it before, it's easy to do it again, or to derive it. And basically, for most people, you're better off just memorizing the formula. It's very close to Pythagorean theorem. C squared equals a squared plus b squared. You've just got this thing that kind of looks like a middle term, in my opinion. That negative 2ab cosine C kind of reminds me of a middle term. Otherwise, it's Pythagorean theorem. C squared equals a squared plus b squared. That be that.